don't all have to think the same. In fact, it's good if we don't. So, what we did in the prac was you had a solution and you electrolyzed the solution and you reduced a certain amount of copper, didn't you? And we know that there is this relationship where if we increase the charge, then we're going to increase the mass of metal reduced. And if you look on page 24, we can see that there are two things to consider. We need to consider the atomic mass of an element, a metal. We also need to consider the number of electrons that are involved in reducing that metal. So with Faraday's law, which is on your formula sheet, we're talking about moles of electrons. This is just Faraday's constant, so we don't need to worry too much about that. What we're doing here is we're changing the scale, if you like, of the relationship between the electrons and the current. So hopefully you remember from phys sci that this is current. What is current? What does current mean? Because if we don't really know what current is, we're going to really struggle with working out what's happening with these. Current is like a gate. Okay, just say this is my wire, and I've got electrons in it. Because this is my copper wire, I'm also going to have my metal cations present. Okay, but it's the electrons that can actually move. If I attach this to a power supply, or I have some kind of charge differential, then the negative charges are attracted towards the positive end, and they are repelled from the negative end, aren't they? Okay, because like charges attract, opposite charges repel. In a wire, only electrons move. Alright, so here we've got our electrons, they're moving past my gate. How fast they move past the gate is the current. In one sense. So I'm going to change my word there to charge. Because in physics, guess what the physicists do? They talk about the movement of positive charge. Just to confuse you. So electrons are moving this way. In physics, well, current moves this. Current moves that way. Okay, so the rate's the same, it's just the sign that's different. Sorry, but these are the rules that we have. So chemists, we're happy to talk about electrons because that's what's actually moving. Physicists, oh no, because of the right-hand rule and other rules in physics that they don't want to let go of, this is a definition, if you like, that current, we draw it as a vector here, or we can indicate the direction with moving away from the positive charge. Okay? But current here here is that rate that's happening. All right, and then this is time in seconds. Current, the measure of current is the ampere. So that's a capital A, and seconds is lowercase s. Okay. Now, because if we look a little bit closer at what IT is, this is the charge, the rate of movement of the charge. So charge is given the symbol either lowercase or uppercase q, it depends. Okay? So if charge is q and current is the rate of movement of q over time, then current is q on t. And then in this arrangement here, q on t times t just gives me q. Are we all right with that? So q equals IT. And you might have remembered that from phys sci as well. Okay, charge. And this is the rate of movement of the charge, and this is time. Right, so that's how these relate. And I always remembered this equation as quit, because by the time you get to that stage, you feel like quitting. All right, so there we go. We've unpicked that equation, but what we need to do now is think about, well, how do the electrons relate to this movement of charge? Well, they relate like this, don't they? Let's just clear that off. Because the next thing that we need to think about is, well, how much mass of our metal are we going to reduce if we run a certain current for a certain length of time, which is what you did in that practice. So if we work through example 1 together, we've got an aqueous solution of nickel sulfate. So this tells me that I know I've got nickel ions and I've got sulfate ions present. And I'm electrolyzing it with a current, 0.258 amps. Time is 2 hours and 35 minutes. Well, I know I need time in seconds and I need current in amps. The amps are fine, but I'm going to need to change that time to seconds. So hopefully we all know that there are 60 minutes in an hour and 60 seconds in a minute. So I'm going to need, what, 2 times 60 times 60 plus 35 times 60. Is that right? Yep. Now you don't have to do that calculation separately. You can just shove all those numbers into the equation. Okay? Don't waste time with an additional calculation that you don't need to make. The way they've done it in the sample answers is to say, well, I can just change this to minutes. That's going to be 120 plus 35, and then multiply that whole thing by 60. It doesn't matter how you go about it, as long as you remember to convert the time to seconds. And we know our current, and we have our formula for finding electrons. We haven't even thought yet about our nickel. 0.258 times, however we want to write that, divided by Faraday's constant tells me the moles of electrons. Now, to determine the mass of nickel that we can actually reduce on, we need to now look at our half equation for nickel. This one is being reduced. We know we can't oxidize this one anyway, but this is a reduction reaction. Ni2 plus 2E minus goes to nickel solid. Now it's just like a regular chemical calculations. It's a mole ratio. So our mole ratio of nickel ions to electrons is 1 to 2. So how does that rate relate then to this? Yeah, so what we want is this one. That one goes on top in our ratio. The other way, sometimes people do get mixed up a fair bit with this, is to just write it out there underneath and think, well, if that's 1 to 2, what do I need to do to this one to make it the same as that one? And so yes, we have to halve it. This tells us the number of moles of the nickel. And whether you write Ni or Ni2 plus, it doesn't really matter because we're talking about 2 electrons per atom, and that's not going to change the mass. Hang on, 0.01243. Alright, so because of this mole ratio, this is how many moles of nickel we're going to reduce if we have this many moles of electrons moving through the wire to the cathode to be ready there to reduce the nickel 2+ ions. So then we need the atomic mass. So remember that N equals little m on big M, and so M equals N times M. Little m of nickel, 0.01243 multiplied by 58.7 is what's on here. It's close enough. 0.730 grams of nickel. Okay, so remember that wire I drew, moving all those electrons along? Well, every time 2 electrons pop out onto the cathode, then another nickel ion can reduce out of solution. And so on, and so on, and so on. Does that make sense? That's what's happening. Now for part B, we're also asked to determine the mass of oxygen being produced at the anode. So this is our reaction at the cathode. We know that we're not going to be able to oxidize the sulfate, and so that means we will be oxidizing the water that's present, and we want to look at our half equation for that. 2H2O goes to O2 gas, 4H plus, and 4 electrons. Back to our mole ratio again. We have a ratio of 1 to 4 oxygen molecules to electrons. So what does that tell me then about how many moles of oxygen?
Divided by 4.
Sorry?
Divided by 4.
Divided by 4. So it's a quarter. 1/4 times 0.02486. Which is 0.006215. sorry, they're a bit messy. And same process where we want to map with a mass, but remember it's O2, not just oxygen, the atom. So it's going to be 32.0 times that. Gives us 0.199 grams of oxygen.